For this lecture, we will discuss the basic statistical concepts that are used for determining values within quality control as part of the quality assurance plan within the clinical laboratory. The mean is the average of a group of numbers. In statistical analysis, we actually represent mean by using the symbol X bar. So we just write an X with a bar over it. We sometimes use the mean value in order to perform other statistical tests on that same group of numerical values. And then the mean is also used as an indicator of central tendency, which is the distribution of data around a central point or a central value. Now, in this example, a student is performing a manual wet chemistry laboratory in which they obtain 5 replicate absorbance values for the unknown. So using a spectrophotometer, they get the absorbance values of solutions or patient samples, and they have those absorbance values, so they need to be able to determine what is the mean of those values. In order to determine the mean or average of these values, we'll first need to add all of those values up. That gives us a total of 2.15, and then once we divide 2.15 by the total number of values, so we have 5, so that number is going to be represented by n. That's the number of values. So we will take the sum of the values, 2.15, divide it by n, which is the number, and that will give us a mean of 0.43 when we keep those significant figures. And so that means that our mean is 0.430. Another indicator of central tendency is median. The median is the central number in the set of numbers when you actually arrange those numbers in sequential order, so from lowest value to highest value. So what we do is in that set of numbers, an equal quantity of numbers is greater than the median value, and an equal quantity of numbers is less than the mean value, meaning you have equal number on either side of that central value or that central number. The median value may or may not be the same as the mean value, so you could have 2 different numbers for this, or they could be the same number. So in this example, a student is performing a manual chemistry test again, and they have 5 samples that they get absorbance values on the spectrophotometer. So what we want to do is determine what the median absorbance value is. So using those same values, we would need to put these in order of the lesser value to the greater value. So here you can see we've already ranked those numbers from the lowest value to the highest value. So here we have lowest going all the way to the highest. Now the total number of these values is 5, so what we'll need to do is take those sets of values and determine which one of those is going to be the actual median. Now it's pretty easy to kind of determine that when you look at numbers this small, so we know that obviously the middle number, the median number, is the 0.430. However, if we were using a larger set of values, then it may take a little bit more effort to determine that. So in order to determine what your median value is, we take those values and determine if we're using an odd number of values or an even number of values. So in this particular example, we are using an odd number of values. So what you'll do is take that total number and then you will add 1. So that gives us a total of 6. We have 5 values, add 1, that's 6. And then we're going to divide that by 2, which gives us 3. So we know that our third number down that list, so we have number 1, 2, 3. This is the value that will be our median number, the 0.430. So now when we have a set of values that is an actual even number, then we got to figure out, okay, well, how do we determine the median value of those? So once we put those in order, we know that it's going to be somewhere in between, because remember, we got to have an equal value on either side of whatever that median is. So we need same number of values going in either direction. So our median would be somewhere in here. Well, if you have a large value of numbers, again, you're going to have to figure out where that median is. So in order to do that, you take the total number of your even numbers, which is 8 total, divided by 2 to give you 4. So we know that value number 4 is going to be of interest. Well, then we add a 1 to that to give us a total of 5. So we know that our value is somewhere between value number 4 and value number 5. So in order to determine that, we just get the average. So if we add those two values up, divide by 2, that gives us 23.5. So we know that 23.5 does fall right in between these two values. So we have a median for these particular numbers is 23.5. So our third indicator of central tendency is mode. So this is the number that actually occurs most frequently within a group of numbers. So it's whichever number you see often, you see the most. With these particular examples here, these are for glucose values, and what we want to do first is arrange those in order, lowest to highest. So arranging those in order, we've got 70 as our lowest, 76 as our highest. Now if we were going to determine our median, of course we know even numbers on either side. So if we were to work out this equation, we have 8 values, divide that by 2, so we know that value 4 is of interest, and then add 1. Value 5 is of interest, and if we got that average, we would have 72.5 as our median. So to determine our modes, we've got to point out which value occurs most frequently. Now it's pretty easy to see once we put these in sequential order that we did have 72. We obtained the value of 72 twice. However, if you were to write those out and write out, like in this chart format, the frequency, then you could say that you saw this number 1 time, this number 2 times, 3 times, whatnot. And so this might be something that you might have to do if you have a larger amount of values, but obviously we could tell within these values that 72 is our mode. That is the number that we see most frequently. As previously mentioned, mean, median, and mode are all used as indicators of a central tendency, or that central value. If the mean, median, and mode are all the same number, then that group of numbers is said to have a Gaussian distribution, or normal curve, meaning that you have equal number of values that are on either side of that center point. And that center point is going to be your highest point of that bell distribution curve. So you can kind of see where it has a little bit of that bell shaped. So you have that peak, and then you have equal values on either side. When you have equal values on either side, to the left or to the right of that central tendency, then you'll get that nice slope to either side of that central value. So again, that's if all of your values, your mean, your median, modes, are all the same number. Now in the laboratory, we like to assume that all of our data is going to have this nice, pretty bell-shaped distribution curve for any time that you're doing any sort of statistical analysis or anything. However, we do have to kind of keep in mind that in reality, this doesn't always happen. So we've kind of got to start to understand a little bit about QC, what this curve means, and what it means if you start having values that fall outside of this population that we kind of considered to be normal within this curve. And so we're going to talk about this in a little bit more depth of what all of this means. So in the laboratory, we've got to be sure that we're sending out quality results, that the results that we send out, that we're confident in those values. And so we want to make sure that those results are going to be able to properly be used to assess that patient's medical condition and make diagnosis and treatment options. So two terms that we use to describe quality results within the laboratory are accuracy and precision. So with a result to be accurate, it's got to correctly reflect the true value of those results. So in other words, if you have a target value, then you want that target value to be reached for that analyte whenever you test it. And then with precision, this is if you were to repeat that value over and over and over again, you want to try to achieve the same results. So we're looking for it to be as close to the true value, that's going to be accurate, and we want it to be precise. We want to make sure that if we repeat that test over and over again, we're going to get as close to that true value as possible. And so we use this together to kind of assess our analyzers. This is all part of the quality control process to make sure that anything that we send out is getting as close to that true expected result that we can possibly get. So part of that statistical analysis to ensure accuracy and precision is to determine the variance of a group of data. So the precision of a group of numbers is indicated by this variance. And the symbol for variance is actually S square. And so that's the symbol that we'll actually use when we're doing these calculations. So the variance will indicate how close together or how precise the numbers are within a group of data. And so a group of numbers with a large variance would be expected to have a wide range of values. So the larger that number is, the larger range of that value is. And then of course, if your variance is a smaller number, then the group of numbers would be expected to be very close to that particular value. And the smaller the variance of the group of numbers, the more precise that particular test the test is, or that analysis of that group of values is. And so what we'll actually do is we'll go through the steps of determining variance. So to determine variance, there is a formula, and it is a kind of complex formula. It's got a lot of steps involved, and it's very tedious, so we're going to talk through that process. But that formula is S squared, which again represents variance, equals the sum of, so sum of, we've got to add up a lot of data here, X, any number, so that's any of your data points or any of your numbers within that set of or group of numbers, minus the mean of that group of numbers. So our mean again is X bar, divided by the number of those, the total quantity of numbers in that group minus ones. And of course this whole value here, this X minus the mean, is squared as well. So that's a very important step that a lot of people will forget. Just a note, most of your scientific calculators do have a variance function on it that you can use, but it is kind of complex. If you know how to use that function, great. If not, don't worry. There are other ways to do these calculations. There's lots of software tools out there that can help you do this, or you can just do it manually. You could plug it into a spreadsheet to determine these values as well. But first, we will learn the manual method because, of course, if your computers ever go down or you don't have access to the software, then you're going to have to know how to do this manually. So here, let's work an example of calculating a variance. So, of course, here we have a list of values of 10 values that are representing glucose values as milligrams per deciliter. And our first step is to rank these values lowest to highest. So ranking them lowest to highest, we have 87 is the lowest, 105 is the highest. There's 10 values. So of course our median would be somewhere between our fourth and fifth value, would be the average of these two. So this would be 96 for the median. And of course our mode is our number that is represented the most. So in these particular values, it would be 93, that would be our mode. And of course we want to determine our mean. So to determine our mean, we're going to add these up, divide by 10. So now what we need to do is determine the mean of this set of values. And so we need to get the sum of all of those numbers, which gives us 962 milligrams per deciliter for these glucose values. And then we divide that by 10, which gives us 96.2. And of course, if we round that with significant figures, we need at least two places And so that gives us 96 as our mean for this group of values. So now that we have determined our mean, we can actually plug that into our equation for variance. So again, we will plug that in. So we will take the mean and subtract it from each of those glucose values, which is represented by our X value here. And then we'll actually work out the portion that is in parentheses. So our value minus our mean, which is 96. And then we're going to take all of that and go one step further, and then we're going to square those numbers. So this is the part, again, I mentioned that a lot of people forget to square those numbers. And so once those numbers are squared, we get our values here. Now don't worry if you get negative values when you're doing this first part, because as we learned previously, a negative times a negative will give you that positive value. And of course we're going to add all of these up, and then that's going to give us our sum. So with the mean, we're going to do this whole first part right here, and it's easier if you actually do that in some sort of chart like this. Obviously, if you got a lot of numbers, it's great that you have different programs, softwares, analyzer, things like that that can do this math for you, because it's very complicated. So when we've summed all of those numbers, that gave us a value of 254. So again, this whole portion right here that we just did is 254. And of course, we're going to take our total number, which is 10, and subtract 1, which gives us 9. So we're at 254 divided by 9, which gives us a variance of 28.2 milligrams square per deciliter square. So don't forget where we did that square. So that's why you got these little squares here. And that's what our variance comes out to be. 28.2. Now let's talk about what we're going to actually do with that number. So when previously discussing QA and QC in the laboratory, we did mention standard deviations. And so in the laboratory, standard deviations is used to assess the precision of something. And it is represented by the symbol S. And what it is that we actually take the square root of that variance. So that number that we just determined through that long equation gets plugged into another equation. So we basically get the square root of that to determine what our standard deviation is. So now that we actually have that variance value, we need to actually plug it into the equation and determine what our standard deviation is. So here we had our variance of 28.2. Plug that into the standard deviation equation. So again, we've already determined all of this that's under the square root to be 28.2 milligrams square per deciliter square. Of course, the square root's going to cancel out those, which is going to leave us with 5.3 milligrams per deciliter for one standard deviation. So this is what one standard deviation is going to equal, 5.3 milligrams per deciliter. When we talk about one standard deviation, or talk about a standard deviation, the smaller that standard deviation is for that group of numbers, then that means the closer those values are going to be to the precision of that mean, or it's going to determine how precise or how close to precision that particular value is. So in this particular example, our mean was 96, which means on either side of this 96 or this mean, for one standard deviation or minus one standard deviation, that means that there's a value of 5.3 in between. So to get from 96 up to one standard deviation, it's actually going to be, doing some quick math here in my head, 101.3 would be what our value would be here for one standard deviation. 101.3 And of course, to get a minus standard deviation, we would have to subtract 5.3 to get this value. So when evaluating QC data, we look at the probabilities of the different statistical analysis. So we look at the probability of a result to fall within a certain level or within a certain amount of standard deviation. So with that data that we get, if we were to analyze the sample over and over again, let's just say 30 times, to establish those standard deviations, then we would know that within 68.2% of the time, then your values are going to fall within one standard deviation. So they're, majority of the time your values are going to hit as close to that mean as possibly can, about 68% of the time. And then within 2 standard deviations, that value is going to hit about 95% of the time, and within 3 standard deviations, 99.7% of the time. So as you can see, majority of the time, your value should fall within 3 standard deviations of your mean. So let's kind of look at this a little bit of a different way. So let's just take, for example, we're analyzing a glucose material or a glucose quality control material, and the expected value or the mean for that particular material is considered to be 100 milligrams per deciliter, and one standard deviation is 5 milligrams per deciliter. So our mean is 100. So our mean 100, and a standard deviation is 5. So that means that anything that we run for one standard deviation, which again 68.2% of our values, should fall plus or minus 5 standard deviation of 100. So that means somewhere between 95 and 105, then that's what we should expect our values to be. So 68.2% of our values are going to fall between 95 and 105, or 32 of the analysis will fall outside of this. So if we think of the 68, a bulk of it's going to fall within that one standard deviation, where the rest of it is going to be outside of it. So 2, 3, or even more standard deviations outside of that value. So now that we've done all those calculations and determined all those values, we got to figure out what do we do with those values. Well, we have to establish what is an acceptable limit for all of those quality control values. Now that we know that we have this set of numbers, what do we do with it? What do we do with these values now that we've determined our mean, our median, our mode, our standard, our variance, and our standard deviation? What do we do with those numbers? Well, we're going to establish what's our acceptable range for our QC values, and that can be referred to a couple different ways. We can refer to it as standard deviation ranges, standard deviation intervals, confidence intervals. So what we're going to do is just kind of refer to it as the standard deviation range or the SD range. And so in order to calculate those, kind of like what we just did on the last slide where we talked about you have your mean and then you subtract that standard deviation to get your lower limit, or you add to get your upper limit. And so we can do this for 1 standard deviation, 2 standard deviation, and 3 standard deviations. So once we know that those limits of what those values are at 1, 2, and 3, plus or minus, then we're able to look at those Westgard rules that we previously talked about when applying it to a quality assurance plan and QC within the laboratory, of determining what's acceptable, what's not acceptable based on those standard deviation and those set of rules. So here, let's just run through another quick example. We're not going to do all that long, complicated math because you will get plenty of practice at doing that. However, let's just say we analyze 20 replicates of a single bottle of QC material for sodium, and we determined that our mean is 140 and that a standard deviation is 3. So what we need to do is calculate what are going to be our 1, 2, and 3 standard deviations, or our standard deviation ranges, confidence intervals for that particular quality control material. So if one standard deviation is 3, then we know that we got to go plus or minus 3 on both sides of this 140. So if 140 is our middle point, then we need to figure out what is minus 3 or a value of 3 for that first standard deviation, which gives us 137. And then if we add 3, it gives us 143 for that range for the one standard deviation. So again, it's 137 to 143, with 140 being that mean, that middle point. So all numbers in between 137 and 143 are considered to be within one standard deviation. Now we look at our Westgard rules. If we had a QC value fall under one standard deviation, then it's considered good and we can proceed with sending out results. So now that we've figured out one standard deviation, let's look at what our additional standard deviations are. So we know that our mean is 140. We know that one standard deviation is 143. And we know that a minus 1 standard deviation is 137. So we got to figure out minus 2 and minus 3. So for our minus 2 standard deviations, then we need to take and subtract an additional value of 3 from this value of 137. So again, we're working our way away from the mean. So subtracting 3 from 137 is going to give us 134, and if we subtract an additional 3, then that's going to give us 131. All right, if we go the opposite way, if we add 3, that's going to give us 146. And then if we add an additional 3, that's going to give us 149. So we know that in order to be within 3 standard deviations, we have to be somewhere in between these values. So we know the majority of our values are going to fall all within this, and that was 99.7% of our values should fall within that range. So the last thing that we're going to talk about when we're talking about dispersion or precision is going to be the coefficient of variation. And so the coefficient of variation is used when you're comparing 2 or more groups of data, and you're trying to determine which one of these has the greatest precision. So you're comparing something to something else and you want to figure out which one is more precise. So the lower the coefficient of variation for that particular group of data means that that data is going to be more precise. So within the laboratory, let's just say, for example, an instrument has a coefficient of variation of 2%. Then of course that instrument would be considered to be more precise than an instrument that had a coefficient of variation of, let's say, 5%. So the lower that percentage, the lower that value, that means that that particular data set is going to be more precise for whatever you're evaluating, whether it's a test method or analyzer, or you're comparing any sort of data within the laboratory. The lower that value, the lower that percentage, the more precise it is. And of course, it's always going to be expressed as a percentage. And that formula is here. So to determine the percent of coefficient of variation, you would take that standard deviation that you've determined with all those calculations, divide it by the mean, and multiply that by 100 in order to give you that percentage. So again, looking at those same set of values, where we've determined that the mean is 96 and the standard deviation is 5.3, then we would take that standard deviation, divide it by that mean of 96, multiply that by 100, and then that's going to give us a value of 5.5% for that coefficient of variation for that particular glucose, that particular QC analyte for that glucose. Now, if we were comparing this on something like different analyzers or different glucose QC material, if we were using to compare to something else, maybe if you're evaluating something else within the laboratory, then that 5.5%, it could be pretty low compared to something else if it's a percentage of, let's say, 10%, or it could actually be pretty high if something else has maybe 1%. So you really got to make sure you do your math correctly to get the correct values in order to be able to assess things within the laboratory.